Welcome to my presentation about the Nobel Prize in Physics in the year 1986. This prize is awarded half to Ernst Ruska for his work on the electron microscope and half or quarter to each Gern Binning and Heinrich Schroner for their work on the scanning tunneling microscope. In the next 25 minutes, I will only talk about Ernst Ruska and the electron microscope, since there is already enough to talk about. In the picture in the middle, you see the young Ernst Ruska working on his first transmission electron microscope in the year 1933. Okay, to start, we have to get familiar with the light microscope, since the basic concept is the same. So, visible light microscope use optical lenses to magnify an object. In the picture below, you see a converging lens. So, from the left incoming light rays, for example, coming from your object, which you want to observe, are focused to the so-called focal point here. And if we draw that lines further to the right, at some point, namely when the Gaussian lens equation is fulfilled, we will get a sharp and magnified image of our object. Now the magnification is depending on the focal length, and the focal length is an intrinsic property of the lens. It's depending on the curvature. So the shorter the focal length, the higher is your magnification, as seen in this equation. We'll see that the number will get negative. This means that your image is inverted with respect to the object. Now, visible light microscope use what is known as a compound lens system. So it means it uses multiple lenses to gain high resolution. How this works? In the schematic, you see the object which you want to observe on the left, and this object is getting magnified by the objective lens here the first time. Now a second lens is used to further magnify this already magnified image from the first lens. And this lens is mostly used, mostly known as the eyepiece of the microscope. The total magnification is then given by the product of each individual magnification, as you see in this equation. Now you can think of multiple lenses in series leading to a theoretically infinite magnification. That is possible, but there is another very important characteristic of light microscope or microscopes in general, namely the resolution. And as you might expect, this resolution is where the light microscope gets to the limit. So yeah, remember, magnification and resolution is not the same. Resolution is defined as the smallest distance between 2 points which still can be separated. So it is the ability to distinguish between two details on your object you're about to observe. In light microscope, light is used to gain information of your specimen. So light is what we know from the electrodynamic course, an electromagnetic wave. And when this wave is propagating or passing through an object in simplest form, just a little opening in a foil or a little hole, it creates a diffraction pattern. This is due to the fact that the wave somehow bends around the corner of the opening, and in every point of this opening, a new wave occurs or is generating and propagating such that interference is occurring. In the image below, we see the diffraction pattern, or better, the intensity profile of such an opening, of two openings which are close to each other. The peaks representing each first intensity maxima. So you see on the left that the two peaks are still resolvable or distinguishable, since they are far apart. And the closer the two holes get, the more we go to the right on the picture here, we see that at some point it's just not resolved anymore since the maximas are overlapping. And this is known as the diffraction limit. And so Ebbe, a German physicist, approximated this limit with his formula that the smallest distance you can get is given by the wavelength of your light divided by the numerical aperture, an intrinsic property of your lenses inside the light microscope. So this numerical aperture is a dimensionless value, which is typically below 1.5 in common light microscopes. And this leads to a typical resolution distance in light microscopes which is higher than 250 nanometers when using visible light. So it is physically just not possible to go below that threshold. Okay. Now we move to Berlin, where Ernst Ruska is born in 1906. He studied electrical engineering in München at the Technical University. On the right, you see a picture of him in his mid-20s. And after his degree in München, he came back to Berlin to join the group of Max Knoll. And the goal of the group was to build more efficient cathode ray oscillographs. So most of you are probably already familiar with an oscilloscope when you did the electronic lab. So the oscillograph is just an early name for that instrument, and it is used to detect time-varying electrical voltages. So this is made by using an electron beam and then applying the voltage you're about to detect on an aperture where this electron beam is passing through, and the higher your voltage is, which you apply, the more your electron beam gets deflected. And your electron beam is then made visible on a screen, and you see the peaks of your voltage, which you want to detect. So we already go into the direction of electron microscope. But first, Ernst Ruska had to do his diploma thesis. He made this in the group of Max Knoll. He had to experimentally prove the Busch's theory. So what is Busch's theory? Hans Busch actually he was a German physicist as well. He actually just solved the differential equation of the electron trajectory when electron is passing through a magnetic field. So electrons are charged particles. So if they travel through a magnetic field, they feel the Lorentz force acting on them. The Lorentz force is given by the charge of the electron times the cross product of the speed and the magnetic field. So what he said out of his solution of this differential equation, he said that axial, symmetric, longitudinal magnetic fields act on electrons like an optical converging lens act on light rays, such that the lens equation known from the optical case is also valid when using magnetic lenses. He said that the focal length is inverse proportional to the integral over the magnetic field strength from object to image. This sounds complicated, but actually it just tells you the higher your magnetic field is, the shorter your focal length. And therefore, since this equation holds true, therefore the magnification will get higher. So Hans Busch himself was not able to prove his theory since he had not good enough equipment. For example, it is important that all of your electrons in the beam have exactly the same energy and the same speed. And this is known as a monochromatic beam. And Busch just didn't have that. This monochromatic beam is, by the way, still a problem in modern microscopes, electron microscopes. And it is called the chromatic aberration. So Ernst Ruska had a more or less monochromatic electron beam and other equipment, since they worked with familiar things in his group of Max Knoll. As a source of the magnetic field, he uses a coil to generate the magnetic field. And to increase the magnetic field strength, he coated his coil with an iron, with iron material with a small gap in it, to create a strong magnetic field on short range. And as seen in the picture here on the right. So in green, you see the wires from the coil where the current is passing through. And in black, you see the iron coating and the small gap here in the middle and the producing magnetic fields. And the axial symmetry just tells you, no matter from what angle you look at your coil, the magnetic field always looks the same. Now, if you have an electron beam coming from the top, passing in vertical direction through your coil, they get deflected by the magnetic field, the same way as light rays get deflected when passing through an object. So yeah, Ernst Ruska got the proof that magnetic lenses exist. He made further improvements then on his iron-coated coil and patented it some years later. He called the lens Pole-Piece lens, or Polschuhlinse in German. And these are still used today in modern electron microscope. So with his knowledge and after his diploma work, he worked on his first idea of an electron microscope. He's inspired by the visible light microscope, by the concept of that, in using a compound system of magnetic lenses. And he got the proof in April 31 that this is indeed possible, also with magnetic lenses instead of optical lenses. On the left, you see a first sketch of his idea. On top, you see the cold cathode electron beam generator, the electron gun. And then here would be the object which you want to observe. So for simplicity reason, he just uses a grid of platinum. And then here is the first coil, magnetic coil or lens, first magnetic lens, the objective lens. And a bit further down is the second coil, which further magnifies the image. And in the right image, you see same the concept and his first images with 17 times magnification. This is not much, but more important, the concept is working. So, fair enough. Remember, Ernst Ruska was an engineer, not a physicist. So he said, and I quote, when I first heard of it in summer 1931, I was very much disappointed that the resolution should now be limited again by the wavelength. So what he meant is, of course, the de Broglie hypothesis of 1925, which states that every moving mass has its own characteristic wavelength. The Broglie wavelength is then given by the Planck's constant divided by the momentum of that moving mass. So in his paper of the year 1932, together with Max Knoll, he estimated the resolution limit of such an electron microscope according to Abbe's limit. He used an accelerating voltage of 75 keV, which leads to the electron energy of 75. He uses a voltage of 75 keVs, which leads to an energy of the electron of 75 keVs. And then he calculated the lambda, the wavelength, by some rearranging, and he got 4.5 picometers for the wavelength, which is way smaller than the wavelength of light. Side note: this is no need to calculate with relativistic effects, since the electron energy is way smaller than its rest mass, with 75 keV compared to 511 keV. As a value for the numerical aperture, he uses 0.02, which he got from earlier measurements, and so he ended up with a resolution limit of 0.22 nanometer, and this is already in the range of atomic distances. And this value was indeed experimentally confirmed 40 years later. To the number of the numerical aperture, he said that this will increase. This net value will also get bigger, so the resolution will also fall down again, and this really happened. So in the year 1933, he works on his first electron microscope with magnitude of 12,000. This is the first microscope which beats the visible light microscope in its magnification. And then he started working at Siemens, where he commercialized the prototype, and the first electron microscope went on market in the year 1939. The scientific results were still rather disappointing, since the scientists then were mostly interested in biological observation with the microscopes. And due to the evaporation of the water, when the specimen or the object is inserted in the vacuum of the electron microscope, most of the biological probes were just unable to observe. And also the radiation damage and the heating of the probe was a huge problem then. However, over the years, they could solve these problems, and the electron microscopes got more and more important in any field of science. So Ernst Ruska got awarded with the Nobel Prize for his fundamental work in electron microscopes in the year 1986. Somewhat late, like he said, and I think I understand that. He was 79 years old. He was mostly awarded due to his early work on proving boost theory and designing the pole piece lens. And another reason for his late Nobel Prize award is due to the fact that the upcoming war during this time, 1940, took the focus onto another field than observing atomic distances. Sadly, he died 2 years later in the age of 81. So now we move away from Ernst Ruska and talk a bit more about the electron microscope itself. So there are two major designs of microscopes, the transmission electron microscope, the TEM, and the scanning electron microscope, the SEM. So transmission microscope means that the electron beam is passing through your sample and is getting detected on the bottom of your whole column. And in the scanning microscope, focus the electron beam before the sample, and then rastering this small focused point, small focused electron beam through your sample, point for point, and you will make an image at every point, and then rendering the total image of your of your sample. So we start to look at how the electron microscope works. So we start at the top with the electron gun, where the electron beam is generated. So there is in modern or in the usual electron microscopes, there is a tungsten wire in pin shape. Tungsten is just wolfram, and when a current is passing through that wire, it gets heat up, and the electrons can emit due to the thermionic energy they get. This is called the thermionic emission. The electrons then get accelerated in a high voltage field. This is typically in a range of 100 keVs to 300 keVs in the transmission electron microscope. And since this is that high because the electrons have to pass through your specimen, and it is about 10 times smaller in the scanning electron microscope, since the detection of in the scanning electron microscope is on the top of the specimen, and so the electrons don't need to pass through. So then there's the condenser coil, which focuses the beam onto the sample with an area whatever is needed here, and then the sample holder. Now, to avoid heating of the specimen, some sample preparation is needed, and the samples need to be very thin, in order of 50 nanometers typically, to not get heat up by the electrons. So the sample preparation in electron microscope is very essential. Then the objective lens is used to focus the electrons coming from the top, coming from the sample, and creating an intermediate image. And then in modern microscopes, there is some intermediate lens as well. There could be more. It depends on the electron microscope you're using. And then the projector coil, which further magnifies again and focus or projects the image on your fluorescent screen or viewing screen. And this is where the image is generated. So, very important, vacuum is necessary in the whole column, since electrons are very light particles, and they would just scatter on all the molecules inside the air. Okay, now the scanning electron microscope. Just a short introduction. Again, you have the electron source and the accelerating voltage. But now the specimen is here on the bottom of the whole column. So, like I said, no thin samples is needed, since the electrons don't need to surpass through the sample. And some scan coil lenses are used to focus the beam onto just one small spot. The smaller the better, and then raster over your sample. And so 1 pixel or 1 point at a time is characterized of your sample. And the types of signal this scanning electron microscope uses is the characteristic X-rays, secondary electrons, and backscattered electrons. We will get to that in a minute. So to see the full potential of the electron microscope, we need to understand the interaction of electrons with any kind of matter. So the more two things interact with each other, the more information you get out of that. So here in the picture, you have an overview of the interactions occurring when electrons hit the specimen. So you see the incident high energy beam of electrons. The sample is here in yellow. So you have the direct beam, for example, you have some elastic scattered electron and inelastic scattered electron. You have characteristic X-rays and backscattered electrons, which are used for, from the scanning electron microscope. So actually you can think of everything that is here on the top is used from the scanning electron microscopes to get information, and everything that passes through here on the bottom is used from the transmission electron microscope to create the image. So I will now talk about the most fundamental or basic interactions to get some more detail and to see how images are created from that interaction. So start with the elastic scattering, where the energy of the incoming and the outgoing electron is the same or almost the same. This is when column interaction is happening. So when the incoming electron is scattered or deflecting due to the positively charged nucleus. And of course, you have the same energy if your electron is not getting deflected at all. And this interaction is used in the bright field image in the transmission electron microscope, and the name is the mass thickness. The name of the method is known as the mass thickness contrast. So how does this bright field image work? You have a so the bright field image, like I said, uses only direct electrons for the image. So it uses no diffraction or scattering. You have in the picture here on the right, you have your specimen, which you want to observe here, and the light or the electron rays which going through and getting scattered or direct beam. And then you have your first magnetic lens, and after this lens there is an objective aperture which blocks all the electron rays except for the ones which are not deflected at all. And so you will create your image on the bottom just with the electrons which are not getting deflected. And the likelihood of an electron to get scattered or deflected is increasing with the thickness and the atomic density of your specimen. So you will get, like I said, information about the mass and the thickness of your specimen by using the bright field image. Now we have the electron, another interaction. The electron is viewed as a particle, and so inelastic scattering occurs, and this is when the incoming electron loses energy. So there is a possibility that the high energy incoming electron is kicking off an electron of an atom inside your specimen. And if this electron is an electron of the k or l orbital, then this free place would get so an electron from a higher orbital state would jump onto this free place, and due to energy conservation, an characteristic X-ray would get generated, which can be detected, and then you can get information about the atomic, what kind of atoms are inside your sample. And like I said, this is used in the scanning electron microscope. Now we use the electron's wave characteristic. If you have a crystalline structure in your material, then you know you have any symmetry which you can use or which you can detect. So a symmetry structure or a repetitive structure in real space can be Fourier transformed, as shown in the picture, to the so-called reciprocal space, where the symmetry is representing by discrete points in your reciprocal space. So a symmetry in real space is described as discrete points in the Fourier space or reciprocal space. Now you can make use of the Laue condition, saying that the wave vector of your scattered electron minus the wave vector of your incoming electron, as shown below, is equal to some distance of two discrete points in the reciprocal space. You will get diffraction. So the Laue condition can be used to detect these discrete points by checking just certain directions of the outgoing electrons. And this is then giving you information about the crystalline structure inside your material. And this is used in the dark field image. So how is the dark field image works? Like in the bright field image, you have an aperture with a hole in it, but this time the hole is misplaced to desired distance. And this aperture now lets only some scattered angle electrons passing through, which creates a dark field image. And this dark field image now gives you information about your structure, crystalline structure inside your material. Here is a real image of a bright field image and a dark field image from the same area. So in the bright field image, you see the mass thickness contrast. The white regions is where the electrons are just passing through. So much of electrons creating light on the screen below, since they get not deflected. And you see here starts your crystal, your structure, or your material which you want to observe, and then it's getting darker or more dense when you go to left upper corner. On the right, you have the dark field image. You see it's dark, and so there is no information about the thickness or the density, but you get information out about certain crystalline structure inside your material. Yeah. So I want to mention that there is still, I come to an end of my presentation, and I want to mention that still nowadays there are there are many improvements made on the electron microscopes. For example, in the year 2017, again, a Nobel Prize is awarded for the development of the cryo-electron microscope. This made the observation of biomolecules possible inside the electron microscope. And the Nobel Prize is awarded to Jacques Dubochet, a Swiss physicist working in Lausanne. And he succeeded in vitrifying water, so he could cool down the water so rapidly that the structure didn't change at all, so the biological probes can be observed in vacuum. And then Joachim Frank also is awarded. He developed an image processing method in which the electron microscope's fuzzy two-dimensional images are analyzed and merged to reveal a sharp three-dimensional structure. And also Richard Henderson was awarded in succeeding in using electron microscope to generate a three-dimensional image of a protein at atomic resolution. So as you see, there are still improvements going on. And to end my presentation, I want to talk about the COVID-19 again. Cryo electron microscope researchers were able to determine the structure of the SARS virus. And you see a computer rendered image below with the crown-like proteins, which gave the coronavirus its name. And with that, I want to end my presentation about Ernst Ruska. and thanks for listening.